Have you ever heard the crackling of electricity on a dry day with dry comb? Why this comb attracts small pieces of paper? Why a balloon rubbed with a woolen sweater or a coat stick to the wall? Similarly, you must have noticed that a glass rod rubbed with a silk cloth or an ebonite rod rubbed with a woolen cloth is able to attract small pieces of paper. In each of these cases, each object becomes electrically charged. Now, the question is how these become electrically charged. To understand this, we have to recall the structure of atom. We know that there is a very small center of the atom called the nucleus. It contains protons and neutrons. Protons have a positive charge, but neutrons have no charge. The electrons carry a negative charge and they may be crudely pictured as moving around the nucleus. The size of the charge on an electron and on a proton is the same. The number of electrons and protons are also same. This means that the positive charge of the proton is balanced by the negative charge of the electrons. Therefore, the atom is neutral or uncharged. What happens when we rub this glass rod with the silk piece? Compared to the glass, silk piece has a greater affinity for electrons. So, in this case, the glass rod will give up electrons to the silk. Hence, the glass rod will become positively charged and the silk will become negatively charged. Similarly, ebonite rod has a greater affinity for electrons than the wool. Therefore, when we rub an ebonite rod with wool, the wool will give up electrons to the ebonite rod. So, the ebonite rod will become negatively charged and the wool will become positively charged. Thus, we have seen how do objects become electrically charged. Now, we can discuss two very important properties of electric charge, and the first is quantization of electric charge. Now, what is quantization? Quantization of electric charge means that any charged body, large or small, has a total charge which is an integral multiple of charge on an electron. That is, Q is equal to plus minus an E. It means Q can be plus minus 1E, plus minus 2E, plus minus 3E or plus minus NE. For example, when we rub a glass rod with a piece of silk, only integral number of electrons can be transferred from glass rod to silk. No fraction of electric charge have been seen. Another important property of electric charge is that it is conserved. Now, what is conservation? Conservation of electric charge means the total charge of an isolated system does not change. To understand this property, let us again consider the example of charging of an glass rod. When a glass rod is rubbed with silk, the amount of positive charge acquired by glass rod is exactly equal to the amount of negative charge produced on silk. the algebraic sum of charges on glass rod and the silk before and after rubbing continues to be 0. Thus, there are two types of electric charges, positive and negative. Positive charges are those which loses electrons, and negative charges are those, negative charge bodies are those which gains electrons. Now, charge a straw by rubbing it with your hair. When we charge this straw by rubbing it with our hair, and we charge one another straw and rub it with our hair and support it like this, and charge the another straw and rub it with our hair and bring it closer to this supported straw, let us see what happens. See what happens. Two similarly charged bodies repel each other. So, we can say like charges repel. Now, charge a glass rod with the help of silk piece. When we charge this glass rod with silk piece and bring it closer to the same straw, supported straw, let us see what happens. See what happens when we bring this glass rod closer to this supported straw. Two unlike charges attract each other. So, we can say unlike charges attract and like charges repel. The attracting and repelling forces between the charged bodies occur because of the electric field present around them. Pictorially, we can view this electric field in terms of electric lines of forces. Now, the question arises, what are these electric lines of forces? A line of force in an electric field is a curve such that the tangent at any point on it gives the direction of the electric field at that point. It is the path along which a positive test charge moves in an electric field if free to do so. To understand this definition more clearly, let us consider an isolated positive charge Q. A small positive test charge Q would experience a force of repulsion. From symmetry, it is evident that the direction of the force upon a positive charge anywhere near Q would be radially away from it. Hence, the lines of force of an isolated positive charge go straight out in all directions from the positive charge, and the lines of force of an isolated negative charge is towards the charge. The direction of lines of force between a positive and negative charge is from the positive towards the negative. The lines of force about two positive charges is shown like this way. Presence of electric charge on any body can be detected with the help of a simple instrument called gold leaf electroscope. What is this gold leaf electroscope? This is a gold leaf electroscope. It contains a vertical metal knob, metal cap or knob on the top, two very thin gold leaves or strips of aluminium, very thin strips of aluminium attached to the bottom end of the rod, and this rod is enclosed within a glass jar and is insulated from the case. When the electroscope is uncharged, the two leaves hang parallel and vertically downward because of their own weight as shown here. Suppose now we touch the metal knob with a charged comb. First of all, charge the comb by rubbing it with the hairs and then bring it closer to the metal knob. Now see what happens. And touched with this knob, let us see what happens to the gold leaves. In this process, the charge flows from the charged rod through the knob of the electroscope onto the gold leaves. The electroscope is said to be charged by conduction. If we touch the knob with a positively charged glass rod, electrons would flow from the electroscope into the rod, leaving the electroscope positively charged. We can also charge an electroscope by induction. Let us see how we can give an electroscope a positive charge by induction. Bring a negatively charged rod near the electroscope so that there is an induced charge on the leaves. Momentarily earth the knob, allowing the electron on the leaves to escape the earth. Remove your finger and then the rod and the electroscope is left with positive charge. Let us repeat the process with actual experiment. First of all, charge the comb with the hair. And bring it closer to the metal knob of the gold leaf electroscope. Don't touch it, just bring it closer and touch the knob with your finger. Remove the finger and remove the comb. The electroscope is charged positively. To give an electroscope the negative charge, we should repeat the process but use positively charged glass rod. Remember, when we touch the knob this time, the electron will flow from our finger to the knob. Thus, we have seen that if we have to charge anybody positively, we have to remove electrons from it. But if we have to charge it with a negative charge, if we have to develop the negative charge on anybody, then we have to shift electrons to this body. Now let us investigate the force exerted by one charged body over the another charged body. Charles Coulomb first of all given us a law to determine this force. According to this law, the force of attraction or repulsion between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. The direction of the force on each charge is always along the line joining the two charges. To express Coulomb's law mathematically, let us consider 2 point charges, Q1 and Q2. For simplicity, suppose Q1 is located at the origin and R is the position vector of the charge Q2. Now here Q1 and Q2 is greater than 0 means that both the charges are either positive or negative, and in both the cases their product will be greater than 0. And in the second case, when Q1 Q2 is less than 0, it means both Q1 and Q2 are dissimilar and approaching each other. The force on 2 due to 1 F21 is equal to K Q1 Q2 upon R square R21, where R21 is the unit vector pointing in the direction from 1 to 2, and the force on 1 due to 2 written as F12 is equal to K Q1 Q2 upon R square and R12 with cap. Here unit vector R12 is pointing from 2 to 1. Here K is the constant of proportionality whose value depends upon the units in which F, Q1, Q2 and R is expressed. In SI units, Coulomb is the unit of charge, and K, the constant of proportionality, is expressed as 1 upon 4 pi epsilon naught. Here epsilon naught is another constant known as permittivity of vacuum. In SI units, the value of this K is 9 into 10 raised to the power 9 Newton meter square per Coulomb square. We find epsilon naught is equal to 8.85 into 10 raised to the power minus 12 Coulomb square per Newton per meter square. Thus, F21 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square with unit vector R21, and F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square with unit vector R12. Please note that these equations hold good only in vacuum, and if the charge bodies or charges are kept in different medium, these values changes and the force exerted will also have different values. Now let us compare the electrical forces with the gravitational forces. Both the forces have inverse square distance dependence, but electrical forces are attractive as well as repulsive, while gravitational forces are only attractive. Moreover, gravitational forces are negligible in comparison to the electrical forces. Now to check it out, let us do one another experiment. Let's charge this comb. And bring it again to the small pieces of paper and see what happens once again. This is the reason that a dry plastic comb run through your dry hair on a dry day can lift a small pieces of paper upwards and thus overcome the force of gravity exerted by the entire earth on the paper. Now to recap, we have learned there are two types of charges, positive and negative. We have also learned about the quantization of electric charge. The charge on a body can be only an integral multiple of charge on an electron. We learned that the electric charge obeys law of conservation, that is, the total charge of an isolated system is always conserved. We have seen that like charges repel and unlike charges attract each other, and gold leaf electroscope can be used to detect the presence of electric charges. Pictorially, we can view an electric field in terms of lines of forces. The force of attraction or repulsion between 2-point charges can be expressed by Coulomb's law. The gravitational force is negligible compared with the electrostatic force. Now try to find out the reason of following observation. When we polish the dry window on a dry day, very soon we find dust on it. But this is not seen, this is not observed on a wet day. Why? Try to find out the reason. And also try to find out why the